Hello, my name is Aaron Medina. This is my project for CS4380 Embedded Systems. So this project is a driver drowsiness monitoring system. It uses your car's camera to watch your eyes in real time and decide whether you are alert, tired, or dangerously drowsy. And it fires an alarm when you need to wake up. According to the NHTSA, drowsy driving causes over 100,000 crashes per year in the United States. Most vehicles today have no direct eye-based detection. They might monitor steering patterns or lane departure, but nothing that directly watches the driver's eyes. This is the gap the system attempts to fill. Before I show you a live demo, let me walk through how the system is designed. This is a cyber physical system. It has 3 layers. The sensor is the camera. It captures the frames at 30 frames per second. The compute layer is the Python running on a MacBook M1 Pro, and the actuator is the speaker, which plays an alarm when the drowsiness is detected. The feedback loop goes physical world to cyber detection to physical actuation. The driver's eyes cause the system to react and produce a sound that affects the driver. The closed loop is what makes this a CPS and not just a camera app. So the core signal is called the eye aspect ratio, or EAR. It is a single number that describes how open your eye is at any given moment. The formula measures 2 vertical distances across the eyelid opening, divided by the horizontal width of the eye. When the eyes are fully open, EAR is around 0.3. When closed, it drops to near 0. That single number drives everything. MediaPipe gives us 468 facial landmarks per frame, and we only use 12 of them, 6 per eye. As shown in the diagram on the right, the teal dots mark the exact points we measure. So the state machine takes the EAR value every frame and decides which of the 3 states the driver is in. Alert is the most normal state. Eyes open, nothing unusual. Tired triggers when the eye closes for 25 consecutive frames, or when the eyelid droops in the 0.22 to 0.27 EAR range for 40 frames. The droop detection is important because it catches fatigue before the eyes fully close. Drowsy uses a different mechanism called perclose. It looks at the last 150 frames, about 5 seconds, and it asks what fraction of those frames had closed eyes. If the answer exceeds 30%, the system goes drowsy. That 30% threshold comes from NHTSA, research on fatigue-related impairment. Recovery to alert requires 15 consecutive frames of fully open eyes. This prevents the alarm from silencing the moment the driver opens their eyes for a split second. So the system is built in 5 Python modules, each with a single responsibility. EAR.py computes the EAR formula. It takes the 6 landmark coordinates per eye, measures the vertical and horizontal distances, and returns a single float. State machine is where the 3-state logic lives. It uses Python's deque to maintain a rolling window of the last 150 frames for perclose. On the right, you can see the actual compute EAR function. It maps directly to the formula on the previous slide. So lines 4 through 8 compute the distances, and line 9 returns the ratio. Alert uses pygame to play audio on the background thread. The key design constraint is that audio must never block the main loop. If it did, we would drop frames and lose real-time performance. Logger writes 1 CSV row per frame and calls flame flush after every write, so no data is lost if the program crashes mid-session. And then main is the entry point. It opens the camera, runs the frame loop, and ties all the 4 modules together. It handles the keyboard input for the HUD toggles as well. So it's important to distinct EAR versus perclose. EAR and perclose serve different purposes, but they work together. So EAR is a frame per signal. EAR is a per frame signal. It is binary. Either the eyes open, drooping, or closed for that frame. It catches single slow blinks and early droop. Perclose is a time domain signal. It does not care about single frame. It asks whether the driver has been closing their eyes too frequently over the past 5 seconds. A driver who keeps microsleeping will push perclose above 30%, even if each individual closure is brief. And then ear triggers tired early. Perclose confirms drowsy over time. Together they cover both the immediate and sustained dimensions of drowsiness. So now we'll start with the live system demo. So you can see the live feed here. The system is in alert state shown by the green text at the top. The ear value is updating in real time, currently around 0.3, which is a fully open eye. So notice that normal blinks do not trigger any alarm. The ear drops momentarily during each blink, but the state stays alert. The blink counter in the data panel is incrementing each time. So now I will simulate a tired driver. So tired triggered without my eyes ever fully closing. This is because the system detects eyelid droop before full closure. The ear stayed in the drooping zone between 0.22 and 0.27, long enough to flag as fatigue. This is the early warning capabilities that a purely closure detection system would miss entirely. So now I will simulate a severely tired driver. So the system has escalated to drowsy. You can see the red border, the urgent alarm audio has switched, and the perclose bar at the bottom of the data panel has filled completely, which means it exceeded 30%, meaning my eyes were closed for more than 30% of the last 5 seconds, which is the NHTSA threshold for dangerous cognitive impairment. Also notice that the state duration counter next to the status text, it shows how many seconds the system has been drowsy. So I'll become drowsy again. So when the driver becomes alert again and keeps their eyes open, the system resets to alert. Recovery requires 15 consecutive fully open frames. The perclose bar is draining gradually as the recent window closure washes out the rolling window. So let me just quickly go through the HUD toggles. Pressing L shows the 12 media pipe landmarks we track on each eye. These are the exact points used in ear calculation. Pressing D hides the data panel for a cleaner view. And then pressing I flips the camera mirror. In a real-world vehicle installation, the camera would face the driver directly. So this toggle simulates perspective. And then Q to quit. Okay, so when the session ends, the system prints a summary. Total duration, blink count, final state, and where the log was saved. Every single frame of that session was logged to a CSV file. Each row has the timestamp, ear values for both eyes, perclose ratio, the current state, total blink count, and how long the system has been in that state. When the logger uses flush after every row right, which means no data is lost even if the program crashes mid-session. This satisfies COPA's principle from our course material that every anomaly should be recorded for post-incident analysis. Here, I'll show it on the terminal real quick. Oh, awesome. So right here. So, like any real system, this one has limitations. The ear threshold is fixed at 0.22, which works for most people, but a production system would calibrate this per driver at session start. Things like sunglasses completely block the eye landmarks, and low lighting reduces detection confidence. So probably an infrared camera would solve both. For future work, the most impactful addition would be a CAN bus output. This would let the driver send a signal directly to the vehicle's lane. It's keeping, assist, or automatic speed reduction when drowsy is detected. That takes this from a monitoring system to an intervention system. So to summarize, this system demonstrates all the core elements of a CPS. a sensor measuring the physical world, a real-time compute pipeline making safety-critical decisions at 30 frames per second, and an actuator providing feedback to the driver. It uses ear thresholding for immediate detection and perclose for sustained pattern detection. It logs every frame. It runs fully on device with no cloud dependency and no custom model training required. It was built in Python using only 5 modules. Thank you. I'm happy to take any questions.